Hello, yes. How are you? Welcome to another video on quantum mechanics lecture. This is lecture 3 and today I'm going to talk about generating functions and Poisson bracket. Before I'm going to start, I have to ask that whether you have any problem regarding our previous lectures and so on. Because if you have probably seen my previous video, I had discussed the Lagrangian, derived the Lagrangian equation that is called Euler-Lagrange equation. And also from there, we have formulated how we can find out the Hamiltonian equation. And most importantly, we have seen that how to use Hamiltonian equation to formulate, to find out the equation of motion. Now today, in this video, before I'm going to start to another section of generating function and Poisson bracket that is most important part of the Hamilton mechanics. Do you have any doubt regarding my previous lectures? So if you have no doubt, then I am assuming that you have no doubt, and if you have doubt, please kindly comment it. I will try to make another separate video to discuss those comments, those your doubts. And secondly, that I have not yet get too many responses, although people have seen my video around till now, more than 200 people have seen this video, but they have not posted any kind of comment and so on. That's why in this video I'm not going to able to show you any particular comment of anyone. Let's get started. Now, what is generating functions and why I am talking about the Poisson bracket? That is the most important part. You see, in the previous lecture, we talked about the Lagrange equation or obtain the equation of motion from the Lagrangian equation. And from there, I told you that if Lagrangian, if the total derivative of Lagrangian is going to be constant, then I can easily construct the Hamiltonian, and this is becoming PQ minus the Lagrangian, where P is the momentum, Q is the coordinate, Q dot becomes the generalized velocity, and L for the Lagrangian, right? And the L was defined as kinetic energy minus potential energy, and L depends on mainly Q and Q dot. Okay, you can also include time explicitly, but there is no problem. We should not, we may and we may not. On the other hand, when we have formulated H, right, it becomes the it then depends on P and the Q, that is momentum and coordinate. So these are kind of transformation that we have seen from Lagrangian to Hamiltonian. And in the Lagrangian we have a very particular interesting thing, that delta L over delta Q minus d by dt of del Lagrangian over delta Q dot, right, is equal to 0. This is what we have already found out in our previous video, and this is called the Euler-Lagrange equation. And we understood that if I have this delta L by delta Q dot, it will simply become the generalized momenta, right? So if somehow the Lagrangian does not contain any Q, there is no Q, right, then it simply becomes delta L by delta Q would become 0. Then what will happen? It simply says that delta dP over dt, or delta P or by delta T, in this case maybe, would become 0, right? Now, if this becomes 0, it simply signifies that the corresponding generalized momentum, whatever the momentum, it becomes linear momentum, angular momentum, or any other quantity, it would be constant, right? And this is, it's constant, it's actually telling you that if your angular momentum is going to be constant, or the P becomes an angular momentum, it means an object is moving in a rotational motion. It's no longer all angular, it's no longer in the linear motion. Therefore, this quantity is kind of very important right over here. In order to differentiate that how the motion is taking place, right? Suppose that somebody has given you some kind of Lagrangian, then your first job is that, can I find out some constant quantities? The constant quantity means that over here, can I find some generalized constant momenta, right? If I know somehow what are the momenta, the generalized momenta, I can easily predict that what kind of motion the particle would have, right? And that is kind of very interesting one. All right. Now, one of the key thing you have understood that if I know somehow what is this constant quantity, then this second order differential equation, why this is second order differential equation? Because over here you may see, let me just write in the partial case. You may see over here, this is del L over del Q dot, and there is again derivative. It would become the second order derivative equation, right? Delta by delta T and delta Qi, sorry, Q dot, correct? Now, you understand it is easy to solve first order differential equation, but very hard to solve second order differential equation. All right. So if you play with some kind of complex system, then you will going to get several set of complex. It's not, I don't mean complex by iota, I mean that the complex structure, right? It can be like d2y by dx square, maybe something 1 by y, or something exponential x, and so on and so forth, right? And it will, it has some kind of very complicated structure. Therefore, whenever we got this differential equation, particularly in second order, it is not going to be easy to solve, but it becomes easy. You can see over here that if I find out somehow that, I got delta L by delta Q, that is going to be Venice. If I have this type of constant, it's simply telling me that the corresponding conserved, there is a corresponding quantity is going to be conserved. There is a corresponding, angular momenta, or there is corresponding generalized momenta that is going to be conserved. It simply means that if I have some structure, let us just a Q and Q dot, right? Let's say that I have q1 dot, q2 dot, and suppose I have only q3 dot, then I can simply say that, if you will evaluate delta q by delta 3, it is going to be 0. Therefore, the generalized momenta is going to be constant. And this can make my job easy. So what I'm trying to emphasize that if I have a Lagrangian of any complicated system, our first job must be that is there any kind of quantity that is going to be a constant, or I have to find out that is there any cyclic coordinate, because cyclic coordinate are those coordinate in which the Lagrangian does not depend on. You see that I have q1, there is a q1 dot, q2 dot, but there is q3, there is no q3 dot, but there is no q3. So q3 in this case will become a cyclic coordinate. And if I have the cyclic coordinate, my job to find out the equation of motion is going to be easy, because what I want to find? I want to find how the trajectory is going to evolve. In this case, what I'm going to give you is, it will give me simply f is equal to ma for this particular case. Therefore, it will be like d2x by dt square plus so on and so forth, right? But our final job is to find out what is the solution of x. If you have some complicated structure of differential equation, you are not going to get this particular x, right? Are you understanding my point? Therefore, I have to find out that, okay, can I get this Lagrangian that is not depending on cyclic coordinate? Now, similarly, you said that, okay, I have Lagrangian, yes. Then with the Lagrangian, I got also Hamiltonian. Then why not we can, work with Hamiltonian? Because if I work with Hamiltonian, then I can easily say that delta H by delta Q would become minus P dot, and delta H by delta P would be, let's say, Q dot. But again, although these are the equation of motion, and from that you can easily find out, but in the end, by taking maybe some time derivative, what you are going to get? You are again going to get the equation of motion, d2x by dt square plus so on and so forth is equal to 0. Either you start from Lagrangian or Hamiltonian, the end result is going to be same, right? They have different framework, all right? But in the end, what you are going to get is the equation of motion. And hence, your job is not going to be simplified, no matter which picture you want to start with. Therefore, the idea is that, can I have cyclic coordinate? Then you may say that, okay, It depends on the question. It depends on the question. It depends on the problem, the structure of the problem, that I can have the cyclic coordinate or not. But let me just rephrase this one. Can I have some way to make this cyclic coordinate? Can I generate myself some kind of a cyclic coordinate? Now, let us say my original space, phase space variable, as I told you that h depends on q and p. So can I somehow transform this Hamiltonian into new Hamiltonian that will become q and p, and somehow this q is going to become unavailable in this new Lagrangian or in this new Hamiltonian. If it is not going to be there, then what will happen? This delta h by delta, so therefore this becomes delta k by delta q would be 0. And let's say that this is basically going to give you the speed, or delta q, delta k by delta q. Let's say I will get the speed dot. And if there is no q there, I got 0 over here, and the momenta is going to be constant. If I have this kind of situation, then getting the equation of motion is very easy. So, what is the job that I am looking for? I am looking for that can I somehow find the equation of motion without actually solving some kind of a particular second order differential equation. Because solving differential equation, obtaining the solution from second order differential equation is a nasty job. And I want to make it simplify. And the way to do it and way to get this simplified is from the transformation of the coordinates. In this case, I got Hamiltonian. Starting from Hamiltonian, I got the coordinate as well as the generalized momenta, and I am together. Although they are linearly independent, therefore I have to transform together. I cannot just say that okay, if I just simply q I'm transforming, then my job is done. No, I have to transform simultaneously this q and q in, let us say, bigger capital Q and capital P. Consequently, my Hamiltonian is going to also be going to change. But this Hamiltonian, the new Hamiltonian that I am going to find, will be independent of some particular coordinate. And as this will become independent of the coordinate, it would become a cyclic one. And if I have the cyclic coordinate or cyclic coordinate, then the corresponding momenta is conserved. And hence, I will find out the equation of motion. Right? And once you are going to do this kind of job, this kind of algorithm you are going to follow, that what you are going to end up, you are going to end up with something called generating function. Let's say the generating function is called f, and f will depend on some original quantity, original coordinate and momenta. This is called original, and let's say that this is basically give me a transformed one, right? So f has to be depend on some original as well as the transformed quantities, combination of mixed combination of the coordinate and momenta, right? Some it will contain some original and some transformed one, and I will get some generating functions. And these generating functions will eventually have something, some constraint that how this q and p are going to be related, that is eventually going to give me the new Hamilton of the system. And hence, the job of solving this complicated differential equation is going to be handled. So this is a very new kind of theoretical framework in which our job is to avoid somehow this complicated looking differential equation, right? And because of this, what I am trying to show is that somehow I have to change the coordinates and the momenta into some different q and p. From there, I must have the new Lagrangian that is going to be independent of the coordinate. As a consequence, the corresponding momenta is going to be conserved. If I know what is the newly Hamiltonian and the corresponding equation of motion, then I can easily get back the solution of this original one. No problem. Therefore, we can easily avoid solving any nasty differential equation. So you see the origination of the generating function is due to something called solving a differential equation. All right, and this can be done easily in Hamiltonian mechanics. Okay, so let's just give you briefly that okay how we can just do it, right? So what I'm basically trying to do is following. I have h that is going to depend on the original, let us say, momentum and coordinate. Momentum is denoted by small p, and there is a small q for generalized coordinate. Now these are called phase space variable, right? Now you may see, now what is the meaning of phase space? In the phase space, you got something over here q and you got something. And in the phase space, you can easily track down that how a particle is going to be evolved. And if you know if you have constructed, if you have found out the relation between P and Q, your job is done. You will immediately know that how this phase space is going to be evolved, how the particle dynamics is going to be evolved. It's, very interesting. But what is this phase space? Let us say in a Euclidean space or in a usual coordinate system, let us say x, y, z, there is a particle that is having mass m is moving with some velocity v, correct? Therefore, at each and every instant, the way it is going to be evolved, the coordinate is going to be changed, right? X is going to be changed, and consequently, there would be some velocity changes. If x and v changes, you will have the different momentum, right? Now, we are going to use the Hamiltonian structure and try to devise some kind of a phase space that is depending on two independent quantities, that is p and q, and they are going to be somehow interrelated by solving the equation of motion that is we have already done, right? Because delta h by delta q would become minus p dot, and delta h by delta p is going to be q, correct? And from there we can devise that how this quantity is going to be changed, right? Now, any quantity that is going to be changed, or whatever the things that is we are going to see in this momenta, right? We will construct a dynamical phase space or the phase space, and whatever the things that we are going to see the phase space, it will actually tell you that how this particle is going to move in your general space. So this phase space that over here is not something that you are going to see in the real world. What you are going to see in the real world is that some particle is moving in the x and y and z space. Therefore, it will have three quantity x, y, z, and therefore, consequently, it will have three momenta px, py, and pz, right? But using the Hamiltonian structure, a mathematical formalism has been invented or established in which I got a phase space P and Q that is encoding all the information regarding the dynamics of a particle. And from the changes that is going to go over here, I can easily predict what would be the dynamics that the particle is going to have in the real world. Now it is clear that what is Hamiltonian, correct? And now how this equation of motion is going to help us to construct this phase space. But as again I told you that we are going to get the another second order differential equation, and solving the second order differential equation is a very difficult task. And therefore, what I'm adapt is that can I somehow convert this q and p into more generalized, more transform quantity, let's say q and p, and consider it to be q and p, right? These capital Q and capital P is going to be a function of these small q and p's, right? Now, if they are actually going to be the transformed one in such a way that it will produce some kind of a new Hamiltonian that is going to depend on q and p, and will not and will produce somehow a cyclic coordinate. That is our demand. Once I got the cyclic coordinate, getting the equation of motion is kind of easy one, right? But the problem is that how I'm going to get this q and p? Should I have to guess all the time, or is there any particular way in which I can get either? I can get the relation between Q and P. Okay, this is the relation that I am going to get all the time, no matter what the problem is. But Q and P could be arbitrary, right? It could be anything. How do I know that if I'm starting from this H, I will end up this K, and let us say if I do the reverse calculation, I will going to get this Q, H. It is only possible when we have some constraint on this Q and P, right? Now, what is the constraint? I know that this Q and P have the canonical coordinate and they are going to follow this equation of motion. Therefore, if Q and P are somehow the unique transformation and it will generate K, therefore, they must have the similar thing, similar equation of motion. Del Q over del K over del Q is equal to minus P, and del K over del P is equal to minus Q. It has to be minus P dot, right? It means that the new Hamilton will have the same equation also. Now, I know what is the original Hamilton equation. Original Hamilton equation is basically PQ dot minus L, and L is PQ dot. I can always write it as H. Now, where this equation come from? I told you that what is the most fundamental thing? The most fundamental thing is the action. Action that says that L dot dt, and if I take some variation over here, the variation was going to be yielding at these between two endpoints, two limiting factor Ti and Tf, that is defining over here some kind of time. In this time limit, it has to be, the variation should go 0, right? So what's my L? L should be over here. Replace L by this one, Ti to Tf, Pq dot minus H dt is equal to 0. Taking this one is a linear quantity over here, right? Hence, the same thing is going to be applied for another one, right? So let's say that I have a new Hamiltonian which is going to be PQ dot minus the same Lagrangian. Let's say the Lagrangian is not going to be changed because action is there. Hence, I can write this PQ dot minus K. And similarly, I am going to use the same trick to just say that you see PQ dot minus K dt is going to be 0. It might be some different Lagrangian, no problem, you can write different Lagrangian. I'm not saying that it has to be same, but different Lagrangian. Then these two structure must be same. But you see that in the H, there is a most important thing is that at the end point, this Ti and Tf has to be vanished, but which is not going to be applied over here, the K. It should not. And hence, I can say that although I can equate these integrand, but these integrands, because H has the stringent constraint, that is the constraint says that at this endpoint is going to be has to vanish, but it is not going to be applied over here. Therefore, I simply say that okay, these can be same, but with some kind of a functional form that should be over here, and this functional form f depending on the phase space variable, let's say q and p, or maybe anything, let us say q, p, q comma p, and so on, right? Or maybe time, in such a way that the first derivative and second derivative has to exist. This f should not be discrete. This f has to be continuous, as well as its first derivative and second derivative has to be exist. Therefore, I'm telling you that they are not going to be same, but with some time derivative. And let's say that there is some kind of factor that is constant factor. This is also maybe lambda could be equal to 1. When it is lambda is equal to 1, it means that p and q are kind of, there is no any scaling thing happens, right? Let us say that you got a vector quantity and you can scale it up without changing the direction. Let us say it is 2, it becomes 4. So you have this quantity is basically some lambda times 2, right? Lambda times original vector. So this is basically a scaling transformed. Whether lambda could be equal to 1 or could be not equal to 1. It's kind of a non-trivial transformation. The important transformation is over here that you got some phase space variable that is going to be depend on these quantities, right? You can take in such a way that the thing Has to be there. If df by dt is going to be 0, they are the same thing, right? But if it is not changing, then this guy is actually becoming the generating function. And this is very important. This is how the generating function comes. The generating function comes under the transformation from original coordinate and momenta to the newly set form generalized coordinate and momenta, where the generalized function is going to be take the list of generalized coordinates and momenta. And you can have this non-trivial transformation when f would be like some half of the, let us say, if you say that there is a q, p and t, if f only depending on q, p, t, there is no generating function, it simply vanishes. So half of the coordinate must be from original set of variable, must be original quantities, let us say q and p, and the transform one, let us say, have q and p. So half from original and half from transform. So you have the effect of f in this newly formed transform quantities when you have something like qt, maybe f can be pqt, right? Maybe f would become something like, what else we got? Uh, pqt, right? Similarly, p and p and t, right? These are the possible combinations you can construct. Means it has the mixed kind of functional dependence. If they are not going to have these mixed kind of functional dependence, then there is no transformation. It means the newly coordinate and the transform one is going to be coincide, and you are not going to get any cyclic coordinate. The idea of cyclic coordinate to generate is introducing some kind of a functional, some kind of generating function. Now, once we know that, okay, let us say that I have a function, right? I got a function that, let us say, depending on q, starting from this one, qt. Okay, I have this one. Then what will I do? Okay, if you have this one, what is this? You got pq dot minus Hamiltonian, right? Is equal to p q dot minus k. I don't know what is k. But let us say I got f is equal to something f1. This is generating function that is going to depend on this one. Plus df over dt. It is a df over dt. It is the full derivative. When we have full derivative, then what I have to do, it will simply become df1 by del q and simply dq dot. How I've got dq dot? It's dq by dt. Okay. So I'm writing q dot. Similarly, I got a del f over del q dot, and I got del f by del t. Let me just write del f1. Right? Any problem? No. Q dot minus h pq dot k del f over del q. Now q dot, what is q dot? I can write it in terms of Hamiltonian. It simply says, what's my q dot? Q dot, q dot, yeah, q dot. I have to be q dot. Do I have q dot? No, I got this delta h by delta p is equal to q dot. Well, I don't require. Why? Because over here, you see that there is a q dot and q dot. I'm not doing anything over here. And over here, I got this q dot and this q dot. So it's just wastage of time to write this one. I can just say, keep it this left hand side, q dot, it would become delta f1 by delta q minus h. There I got p, and this would become delta f1 by delta q, this q dot minus k del f1 by delta t. Right? I don't have to use the equation of motion from the previous Hamiltonian, right? What I want to understand, there's some kind of a transformation to happen between H, K. And from there, I will devise that, okay, whatever the coefficient that we have got in terms of Q dot or maybe P, these has to be 0 in order to get the complete transformation between H and K. There should be nothing, there should be just only H, K and del F by del T. Therefore, the coefficient of this guy, the coefficient of Q dot and Q dot over here has to vanish. Hence, I will say that P minus delta F 1 by delta Q is equal to 0. And this capital P is equal to, if it vanishes, it simply becomes delta F by delta Q. Let's say it is 0, therefore it becomes negative and positive, right? So now I got, if I know what is the generalized generating function F1, I simply know what would be the momentum. I will take F1 with respect to Q, I will know what is the transformed momentum. Now, since these quantities have vanished, I got the simple relation H is equal to minus K plus del F over del T, or I will write multiplying by minus H is equal to K, or let's say that, yeah, I can just take K over here. I know what is the exact relation. How can I construct H is equal to K is equal to H plus delta F1 by delta T. That's all. So you give me H. Somehow you know what is the F1, what's the generating function, and I can construct the newly Lagrangian. But if I know somehow what's the F1, I can easily get the corresponding generalized momentum in this one. And this tells me that these P and P's are conjugate momenta. Similarly, you can construct your own generating function of any particular kind. Therefore, I told you the list of generating function that can have only f depending on QQ, PQ, and maybe it becomes Q1, Q2, Q3. Similarly, it will have to be become Q1, Q2, Q3. Therefore, the thing is that the mixed combination must be there, right? And similarly, so let me just show you that how we can get another type of generating function in general. Let's say that I got something called F2 Q P T. Okay. Now F2 QPT is there. Therefore, starting point is PQ dot minus Hamiltonian is equal to PQ dot minus K. Take something, let us say del Q F2. Del Q F2 is basically del by del Q. Okay. Writing like this one. Q dot del P F2 P dot del T F2, right? Now over here, I got Q dot Q dot, so it simply becomes del Q F2 Q dot minus H. But now the problem is that I got over here PQ dot minus K, but right now I got delta F2 by delta P, there is P dot. And this is kind of trouble, right? Because I need something to be here. Therefore, what I can just simply say that, okay, let me just write down in this way. Can I have something that cancel out this PQ? Well, it simply says that, okay, PQ dot plus PQ dot. But it is not going to do my job, right? Because I cannot simply add and subtract over here because still I'm going to left with the PQ, right? Well, I can do something. Over here, I got F2 QPT, but can I just say that it also takes P and Q? If it is there, therefore I will over here P dot Q minus PQ dot. Now P dot Q and P dot, I will get one thing over here. And PQ dot would be simply cancelled. Do you understand this situation? Now I got P dot Q. There is nothing over here. I got minus K plus delta F2, let us say P minus Q, that is P dot delta T F2. The same thing is that whatever the thing that is appearing over here, they have to be vanished in order to get the correspondence between HK and F. And I will get P is equal to delta Q. Let me write over here in full form F2 by del Q. And similarly, I will get del F2 by del P. It has to be capital P is equal to del Q. These have to be followed. And hence, I will get minus H minus K del T F2. So K becomes H plus del T F2. It's very simple. So if you give me this kind of generating function, if I know somehow that this is the generating function of this particular kind, that is only depending on Q and P, I know exactly how the new Lagrange, that is K, is going to be there. If I know delta F2, I can easily find out what is the equation of motion without even solving the complicated differential equation that is going to appear. Let me just give you a simple, it's not simple, it's actually simple harmonic motion, right? You all know what is the solution of harmonic simple motion. Simple harmonic motion, a system, a body is attached with a spring having some constant K, right? What would be the kinetic energy? The kinetic energy, because it's like kinetic energy becomes P square by 2m. And let's say that you have given some stretching or compression, let us say at x, it would become kinetic energy. Kinetic energy is half k x squared, right? P square by 2m plus half k x squared. If you would simply find that, okay, why should I solve? I know the solution. The solution is x is equal to a sine omega t plus b cos omega t minus kx and so forth, right? Then what is the use of it? Yeah, it is no use of it. But see that it's very interesting. The thing is that if there is no any friction, this system is going to be conserved. Therefore, h is becoming some kind of a constant, right? And there is a way to solve it. You see over here, there is no cyclic coordinate. If there is no cyclic coordinate, this guy is going to be very complicated. Although it's not complicated, we have already understood. But somehow this would be a part of a very complicated, framework. I know there is no cyclic coordinate. The question is that how can I generate a cyclic coordinate? Well, I can use the following thing. Let's say that P becomes, what else? P becomes something called f of q, right? Or P square. No, f of, not f of P. But let's say that P becomes f of P. I have to remove somehow these cyclic coordinates, f of P cos of Q. Because let's transform this P and X, the generalized momentum and coordinate, into, let's say, P and Q. Okay. So let me just transform this P goes to f of P cos Q, and similarly X would become, what I can say, right? F of P. Let me just again change this thing for you. 1 by 2m P square, small p square, plus 2 is going to be there. So this is kmx square, right? Now, if this is true, therefore P can be transformed into f of P cos Q, and X would be like 1 by km. Can I take it into square root so that this guy is going to be wash away, and would be sine Q, right? Hamiltonian. So 1 by 2m, it's basically f square, some function of P cos square Q, some function of this one, right? And this guy would be km, this is km over here, and x square sine square Q. Cancelled. F square, both the places, 1 by 2m, f squared of p cos square q cos square sin square q is there, is gone. It's our new Lagrangian, new Hamiltonian, that is independent of coordinate, right? So we have actually found out some cyclic coordinate, and this cyclic coordinate is just simply gone, right? And from here, I can easily construct what is the generating function. What would be the generating function that can produce this type of transformation? It's pretty simple, right? Now it's pretty simple. Then how we can just do it? Well, I have something like, because P is equal to f of P cos Q, right? And similarly, I took f of P by Km, right? This is what I've done. And this is going to be sine of Q. Now we found that there is some relation that is there. Now you see that why I'm using that particular relationship. Let me just see over here, QQT. Now you see, with this relationship I will get P and capital P, right? So let's say that if this is kind of a generating function, then I can easily find out what is the momentum. So this guy is over here, right? This P is going to give, this P is over here. Therefore, I can easily find out that what would be the F. All right. Now, if you will look at F2 minus PQ, if this type of generating function, then I could have also used this one, F2 by Q is equal to P, because I still know what is my Q. But the thing is that end result would be, no matter what you just going to be used, the end result is going to be the same, right? So let us just use this one, because F1 is simply becoming the Q, Q and T. Therefore, there is no problem too much. So P becomes dF over dQ, right? So let's say this is got P is equal to del F over del Q. Over here, del Q is indeed X. Now P is simply F of P cos Q is equal to del F over del X, right? So P is equal to F of P cos Q, but over here there is X also. Therefore, I can write P by X is F of P is some unknown function. Therefore, I cannot just write over here unknown function, because I have to determine what would be the F of P. I can divide P by X. It will become Km cos Q by sin Q. It becomes cot Q. Therefore, P would be X Km cot Q, right? There is no problem. Hence, I will write over here X Km cot of Q. And remember that Q does not Q depending on X, but Q and all these quantities, that is X, small p, and capital Q, are independent quantities, right? Therefore, if I have to find F, let us see, if I'm writing F, take the integral kx cot Q dx, and there would be some kind of a constant, right? So it simply becomes x square by 2 km cot Q plus C. Now I know what is my F. Now once I know what's my F, I can easily find out another set of thing that is called bigger P, which will tell us that, okay, whatever the F you got, take the derivative with respect to the coordinate Q. And it will simply tell us that, okay, take a coordinate of cot Q. There is, these guys are becoming constant. This is again a constant. There is no problem. If I'm just taking the cot Q, the cot Q would become like minus x square by 2 km. The derivative of cot Q is cosec squared Q, right? And minus cosec squared Q. Therefore, this would become plus. I got x square by 2 sine square Q into km. That is kind of incredible. I exactly know how this P and Q are now related. So as I got this P has relationship between x, k, m2 sine square Q, I can rewrite this one as x is equal to root 2P over root km into sine Q, right? And the question is that what is my f of P? You see, my assumption of x is equal to f of P by km sine Q, and over here I got x is equal to something with sine q. So if I will compare, I will simply get f of p is equal to root 2p by km, right? And this was also km. Hence, I got f of p is equal to 2p, taking this inside square root k square m square km, it simply becomes km. So from here, using this simple formula, I have got what is the structure of this f of p. Indeed. So that is very fascinating, and with this I will get the relationship of h. The new h or k is what? F square of p by 2m, and f of f square is basically 2p km by 2m. It is only pk, right? And you have to understand a very interesting thing, that this is k or this is h. If I'm writing delta k by delta q is going to be constant. So you see, we got the cyclic coordinate, and if delta k by delta q is going to be constant, it is nothing but this p dot, right? Therefore it simply says that this generalized momenta is going to be constant, isn't it? And if p dot, therefore I can easily find out what is, let me just write delta k by delta p. Delta k by delta p would be simply k, and it would be with q dot, isn't it? So I will write delta q by delta t is equal to k, and hence I will get kt plus c. Therefore, I can easily write it over here, the solution of q. Q becomes kt plus c. And you already know what is k. K is m into omega. So you see, k is equal to m into omega, or m square x square half k square m square omega square. Yeah. So q becomes this one. So this is the same as the way you have found out the previously the solution, that x is equal to, will have the simple harmonic motion, and from this relation, whatever this some constant, sine becomes omega t plus c, right? Therefore it is bit complicated. You feel like that it is a bit complicated. Why it feels like that it is a bit complicated? Because we have used the Hamiltonian and cyclic coordinate cyclic function, and the problem is very simple, right? The problem has a very simple structure. We know the solution, but we have taken a different route to solve this problem. That's why it be kind of okay, what, there are a lot of derivatives and so on, but it's not. And similarly, as we know, what is the relation between q and t, actual thing, I have now the generating function equation, right? F is equal to this one, and just put the value of x over here, you will again know how this will look like. So replace q by that one, replace x by that one, then you will know what is the generating function. I know what is the Hamiltonian. So you see that if I somehow divide the cyclic coordinate, then our job is done. We can easily get the equation of motion without actually solving the differential equation. That is the role of generating function. Now, generating function have a very deep structure when we are going to study the angular momentum in the quantum mechanical framework. Similarly, spin angular momentum have the very most complicated, not complicated, but a very interesting framework. That's why the generating functions, the idea of generating functions is very important. And from here, we are again going to use these generating functions to solve the equations in the quantum mechanical system. And if we use this type of idea of generating function from the classical mechanics, then it would become the quantum generators. Quantum generators that will produce some kind of an angular momentum. The generator would become some kind of angular momentum. And you know that if something is if a generator becomes an angular momentum, it means the particle is in a rotation. And it has become too important and too interesting to see that how these ideas can help you to solve most complicated equations in quantum mechanics. That's why we are using these things, we're using these analyses. So as you now understand the role of generating functions and how it is coming into the picture in the classical mechanics, and it's going to play a great role in quantum mechanics, then there is an important question to ask that, okay, you see, why do we do these things? We do these things because to find out that how a quantity is going to evolve, right? Let's say I'm writing some quantity, and obviously this quantity, if I'm writing quantity in the Hamiltonian framework, it is going to be depending on the phase space variable, that is q and p, right? So any quantity, how this quantity is going to change in a phase space is very specific to our job, because no matter where you are, either you in classical mechanics or quantum mechanics, the one particular thing is very interesting, that what will happen to this system, what kind of dynamics we are going to see, right? And can you tell us what is telling me about future? In order to predict the future and how a system has evolved from past to present to future, the time derivative is most important. And there comes that, okay, what is the state of that particular function, or how the state is evolving? It means that it involves that how the phase space is going to evolve. Now, I am not going to give you too much the classical mechanics, which I am going to cover in the particular classical mechanics course, but I'm just give you that, okay, let's say that any quantity q that is depending on q and p, I am write this dq by dt as, let's say, del q by del q, del q by del p, right? Sorry, what I'm writing. It becomes q dot plus del q over del p and p dot, right? Let's say that it is not explicitly depending on time for a moment, and then I can, include, if it is including with time, you may just write that, okay, this becomes del q by del t. But for a moment, let's, ignore this quantity right away. Now you see that I know if I have the Hamiltonian, I got delta h by delta p would give me q dot, delta h by delta q will give me minus p dot. This would become something with Hamiltonian, right? Delta q by delta p, and it would become delta h by delta p. Now, any quantity whose time, how this quantity is changing with respect to time, is going to have a something antisymmetric relationship, right? And this algebra that you have to find the derivative, this can be actually encapsulated in something called the Poisson bracket, where you are writing in the curly bracket, or maybe some people write to use a square bracket, whatever you write. And this is actually telling you that how the quantity is changing with respect to time in a phase space. You take that quantity and Poisson it with h, the Hamiltonian, right? And that is basically telling you that how this quantity is changing with respect to the coordinate, and the Hamiltonian is changing with respect to p. Similarly, changing with respect to p and q. You have to understand that q and p are the independent quantities, right? If you do this, it's going to be changed. Therefore, the whole Hamiltonian mechanics can be easily described from this Poisson bracket. Now, let's say that if this quantity is going to be constant of motion, it is going to be zero. Let's say that, okay, v is not changing, the v is uniform. A particle is moving uniformly. Then let us say q becomes velocity, therefore v and h is going to be constant, because this guy is equal to zero. It says that the quantity in h is going to be constant. It means that whatever the thing that you are writing over here vanishes. It is a very special case. Now, if a particle is moving in a constant velocity, what do we call? The corresponding energy, I understand, is not going to be changed. And it simply says that how the state is going to evolve it. In quantum mechanics, it has different formula, different framework, but it has the similar scenario, that we actually try to find out the position and momenta and how this will happen, how this will affect the energy state and all those things. And this is something is changing, that how the velocity and its Hamiltonian is going to be change. or any particle is moving, how the velocity is changed, I can easily construct a Poisson equation, and it will simply change. Tells us that okay, if this Poisson equation vanishes, the corresponding quantity is going to be changed throughout its dynamics. It has a particular relation. So what is the? Let us say that if I'm not writing h, you can write anything. Let us say u and v. U and v. I will write del u over del q, del v over del p minus del u over del p, del v over del q. This is the definition of the Poisson bracket, right? Now if you interchange u and v, you will end up with one sign. Let us say I have v comma u, then what will I get? I'll simply get, if I interchange these positions, I will end up with delta v over delta q, delta u over delta p minus del v over del p and del u over del q. You see that they have the same structure but with different positions. Del u by del p has to be there, therefore it would be like same thing as uv. So by changing the order, it will pick the negative sign. As I told you that this is anti-symmetric, or what you can just say that anti-Poissonate, right? That if I am changing also q and p, everything is changing, it's so and so forth, right? Similarly, I can construct more thing into it. Let's say that okay, I have generalized coordinate and there is another coordinate, and what is the value I'm going to get? Yeah, you can see that delta q by delta q, delta q by delta p minus delta q by delta p, delta q by delta q. Delta q by q, it is 1, it's going to be 0. Similarly, it's 0 and it's 1, it's 0. I got the same thing if I write p and p. So any two quantities is going to be changed. It's going to be, let's say that it vanishes. Whatever this quantity is going to be take place, the same quantity is also going to be there. So they have now postulated. I just say that when something is vanishes, we say that okay, this is postulated. But what happens if I got q and p? I'll write delta q by delta p, sorry, delta q, delta p by delta p, right? Delta q by delta p and delta p by delta q is vanishes, it becomes 1, right? Therefore, if I want to write in terms of, let's say that in terms of tensor indices I and j, I'll simply write delta I j. Delta ij only give you 1 when I and j are equal. If it is not there, it's simply 0. I is not equal to 0. What is the meaning of it? It says that x and px will be 1, but x comma py 0. Right? A particle is moving in x direction. You can have the same effect. You may just say that okay, I can find out what its momentum is or how the momentum is changing with respect to x, right? But if a particle is moving in a x and I am taking the measurement, I don't know anything about how the momentum is going to change in y. I'm giving you the in the prospect from quantum mechanics, but in the classical picture, it simply says that x and px, they are not postulating, but x and py, they are going to be postulate. The physical structure is come to a point, but just giving you the algebra that actually how these guys are working, right? Similarly, let's say that I got something, I got h, right? Let's say that h is equal to p square by 2m. There is no potential energy. Well, I want to find that what happens with q and h. Q and h is simply tells you that okay, how the position is going to be changing. Therefore, it's simply q is equal to p square by 2m. Now see carefully how I am taking the do this thing. You see, you have to understand that this is basically denoting you the partial derivatives. Therefore, this is constant. I can take it outside constant p square. You know, I can write always p square as p times p, correct? So I can write p times p. Now follow the chain rule. What I will going to do is qp, right? And there is again p over here. And similarly, I can write 2m q. Let us say I have written one p over here, another p stayed this side. Writing this p right over here, another p this side. You see that I know what is qp, basically 1, therefore this is p, and similarly I got p over here. 1 by 2m pp, it will simply give me p by m. dq by dt is basically what? The coordinate over thing is velocity. So any particle that is free to move in a space without any influence, without any acceleration, there is no mgh, or there is no any acceleration applied to it, there is no potential energy, therefore the momentum is just there, isn't it? So momentum is going to be constant. P is equal to m into v, right? So this is how we can easily find out what is the momentum without even doing any particular thing. That is the interesting thing. If I just write p and h, then p and h is going to be 0. It simply says that there is no any acceleration, there is no forces acting on it. Because dp over dt is p comma h. dp over dt, if you do the algebra, it is going to give you the constant, and p becomes constant. You see there, the p, that is what I am writing over here, is a equation of constant, right? Or it's conserved, isn't it? Now, similarly, I have a very interesting relationship over here. Let me just again tell you one important relationship. Let us say I got AU plus BV, and having a Poisson with W, it will write, I can write A U comma W. Okay, if I have AU plus BV comma W, then A is just constant, U comma W, then simply B, V comma W, and that's all. Another important relationship we have, let's say that U, V comma W, then this is simply following a cyclic relationship U, V and W. You write it like in a clockwise direction, U, V, W, then what next? V, W, and then you can simply write W, U, comma V. If you do this way, then the whole thing is cyclically adding, and they're going to cut out everything, and the end result you are going to get is 0. So just to make a circle, put it u over here, u v w, the way you have started, and you are ending up this one. All right. Now, one of the most important aspect I would like to take your attention into is called angular momentum. Now, angular momentum is kind of very interesting, denoted by L. It's a vector quantity, and it's basically r cross mv, right? Or I can simply write over here r cross p. This is the angular momentum. Now, in 3 dimension, I can write angular momentum in a component wise, like I will write over here epsilon I j k. R over here is denoting the position. Let me just write xj, and p is k. What is epsilon ijk? It's epsilon ijk have the permutations ijk. If you just move in a cyclic direction, right? Let us say ijk, jki, or kij. The epsilon ijk having all these things distinct, right? It will always give you 1. And let me just simply say that, okay, ijk, let us say 1, 2, and 3. You mark it as a 1, 2, 3. As long as you are moving in a clockwise direction, the end result is always plus 1. If you are moving in a counterclockwise direction, it will take minus 1. And let's say that if any two quantities, let us say I is equal to j, it would become 0. So r cross p, if you write it in terms of determinant, let us say x hat, y hat, or z hat, write over here x, y, z, and px, py, pz. For Lx, I is denoting I go from 1, 2, and 3. 1 is for x, 2 is for y, and z. So L1 becomes what? I can easily find out without any doing Lx. Let us say I'm writing Lx. It becomes y into pz and z minus py, right? So from here I will get also same thing. Let us say Lx or L1 is equal to epsilon 1. I know that this has to be this combination x2 pk, right? And similarly, because they are going to add up, that what are different combinations, I have to write j becomes 3 and 2. I know that these two things has to be distinct. So in this place j becomes 3, so j becomes 3 and k becomes 2, hence pk, p2. 1 2 3 will always give me plus x2, it has to be p3. P3 means pz, x2 means y, and 132. You see over here, 132 in counterclockwise direction, it becomes minus. X3 is z, and p2 is py. You see, you are going to the same thing, y into pz minus z into py. So in the tensor notations or in the indices notations, I can write angular momentum like this. Let us say I have this angular momentum, but I want to find the positronate. Let us say a particle is moving in a circle, therefore it has some conserved angular momentum or something like that. Let's say I have to find x1 dot, not x1 dot. Let's say that I have some quantity in which the relationship can come, where I have to find x, let us say I, and with angular momentum Lj. How can I write? I'll do simple thing. Xi is there. Lj is, I told you over here, right thing. If I is there, it's called free indices because this is going to dictate what's going to be over here. And jk is simply telling you that because they are, with summing with j, k and summing with k, right? So I have to write epsilon j kl xk pl. Okay. Now, as I told you that these are differential equations, therefore you have to follow the chain rule. I'll write epsilon jkl xk. Over here, I will write pl. Similarly, I write xi, comma, xk is already done, already derivative, taken the derivative. Over here, I will write epsilon jkl, let us say pl, and write over here xk. Now, I already know this is constant, no problem. I already know that x and x is going to be 0. The Poisson bracket vanishes, but xi and pl will have Kronecker delta I into L epsilon jkl, and there is xk, right? You see what I can get over here, I and L, when they are going to be same, then this quantity is going to be survive. Therefore, I can replace L by I, jki xk. So the Poisson bracket of these two things Lj will give me epsilon antisymmetric tensor. This is called Lebesgue tensor, and there is xk. Okay, and you see that let us say x1 and angular momentum. Let us say because I cannot be equal to j. If I is becoming equal to j, this quantity vanishes. Therefore, angular momentum has to be in different direction. X, if a particle is moving in this direction, angular momentum, let us say in the y direction. Okay. If this happens, then what will happen to it? I'll write j is what? J is 2. K, I don't know, 1. What must we go over here? Only 3. And K is summing over here 3. There is nothing because there is one position is left. Therefore, this is the only one combination that is possible. Not you can just write, okay, I have to write all the any sum. No, there is no possible sum over here. Now, 2, 3, 1. In a circle where is 2, 3, 1? 2, 3, 1. It's going to be like this. 2, 3, 1 give you plus sign with x3. So commutation relation with x with angular momentum in y direction will make the particle in going something in outward direction, right? The particle will as if move in the outward direction. That is how you will be facing this one, isn't it? Isn't this very interesting? So you see that very interesting thing can occur if you know how to do the Poisson bracket, and that is have the very interesting role to play in quantum mechanics that we are going to see. But in classical mechanics, when I'm going to take all the classes in classical mechanics, I'm going to go in a very detail and discuss everything, how things are changing, what is the meaning, what is the meaning of generating functions, how we can produce so many different relations, what is the in-depth meaning of commutation relations, or let's say the Poisson bracket, and so on and so forth. All right. So if you have any doubt, please don't forget to write a comment, and I'm going to discuss in the next video. And if you have watched till this video, thank you very much. And so this is the Minute Cap signing out.